Hello, I am Borja Martinavarro, and today I'm going to give my presentation on my third year project on photonic integration for automotive phased array LiDAR. I've separated this presentation into four main sections. Firstly, I will give a small overview on LiDAR systems in autonomous vehicles. Then I will talk about the theoretical research I've taken. This involves optical phased array, LiDAR, and the modulation schemes, and the possibility for photonic chip integration. Then I will talk about my process in designing a LiDAR in designing a LiDAR system. This involves the evaluation of trade-off parameters, um, and then I will give specific details of my system design and signal-to-noise ratio values, etc., etc. Lastly, then I will give a small analysis of my whole project as a whole. So let's get into the overview. So autonomous vehicles have been under development for years now, and LiDAR is one of the cornerstones in autonomous vehicles. LiDAR is basically used to monitor distances to nearby objects. Um, as a result, this system allows the vehicle to assess risks around it, when certain decisions can be taken, when you can change lanes, when you can increase velocity, etc., etc. As a result, LiDAR facilitates many driverless features such as lane keeping assistance and autopilot. So now I'm going to talk about the theoretical aspect of my project. Firstly, optical phased array implementation. Firstly, LiDAR systems were purely mechanical, so they were composed of basically mirrors placed on top of vehicles in order to give a 360 field of view. However, this design is very bulky and very robust, and is not viable to sell to the general public. Therefore, another alternative to mechanical LiDAR is optical phased array LiDAR. Optical phased array LiDAR works by driving a laser source into emitters, which then produce the image of the surrounding objects. The main feature of OPA LiDAR is the phase tuners. Phase tuners allow for beam steering by phase shifting the laser source by a certain amount in order to steer the signal. This is very advantageous because it increases the whole field of view of the LiDAR system. Optical phased array LiDARs are excellent in the near field, so at small distances, as practically the whole laser source is utilized and hardly any power is lost. However, in the far field, side lobes do start to appear. These are basically inefficiencies in the signals. So in the far field, many problems appear, which I will talk about later on in the trade-off section of this presentation. Now let's talk about the modulation schemes. At first, in LiDAR systems, time of flight was the most common modulation scheme. Time of flight basically utilizes the time measurements for a laser source to go back and forth when rebounded from an object, and from there measurements for the distances to those objects were taken. However, again, similarly to mechanical LiDAR, time of flight is a system in which the size of the design is very large, is very heavy, and also is very expensive. Therefore, another alternative to this is using frequency modulated continuous wave modulation. The big advantage of FMCW is that it not only measures the distance to certain objects, but it also measures the velocity of those objects. So in a road, obviously there are stationary objects such as a lamppost, but also there are moving objects such as other cars. And it is very important to know the velocities of those cars in order to assess the risk surrounding the vehicle. FMCW works by modulating the signal through a triangular waveform by varying the frequency. This results into two main signals, which is the transmitted signal and then the received signal. These two have different frequencies, which this change in frequency is then used to calculate the time delay of these two signals, and then later on measurements for the distance and velocities of surrounding objects. Now let's talk about the photonic integration. The main advantage of using optical phased array and FMCW LiDAR is the possibility of including these two, the whole LiDAR system, into a small scale chip. This is very beneficial to solve the issues with size and design of LiDAR systems, and thankfully Silicon Photonics allows to produce photonic integrated. Now let's get into the next section of the presentation, which is the system design. Firstly, let's talk about the trade-offs. The two main trade-offs are firstly the emitter spacing. The main thing with emitter spacing of the optical phased array is that when the emitter spacing is larger than half the wavelength of the laser source, side lobes start to appear. So as you can see in the figure there, the various scenarios where for example, in the image B, the emitter spacing is very large. So therefore, the side lobes, the signal would not give a very clear image. But then, if the emitter spacing is too small, the field of view will be very small. So we have to find a trade-off between these two in order to have a decently sized field of view, and also an efficient output signal. The next trade-off I want to talk about is the bandwidth with the thermal noise. Obviously, in any system, we want the bandwidth to be high. However, as you can see in the figure, there's an exponential relationship between these two parameters. So we again have to make a trade-off between these two parameters. Considering these trade-offs and a few others I made throughout the project, I was able to propose a LiDAR system. In this LiDAR system, I assume we were evaluating a scenario where we want to analyze an object which is 20 meters away. So in this system, I decided to use 2.5 milliwatt laser at an eye-safe wavelength. This is very important in order to not have a very high laser power, in order to increase the efficiency of the system. As a result, by making a few calculations, that I decided by looking at many trade-offs to propose a LiDAR design of OPA of 4x1 with two photodetectors to detect the signal, and this gave me a signal-to-noise ratio of 25.6. As a result, in general, this has been my project. The system design I evaluated seems proper, seems good. The signal-to-noise ratio is appropriate. However, problems do start to arise at large ranges, and this can be something which can be evaluated in the future. Thank you.